In this video, we are going to work out sample exercise 12.2, part C, found on page 484 of your textbook. Part C is asking you to estimate the length of the edge of the cubic unit cell. So I think it's going to be helpful for y'all if you have your book to kind of follow along here and look at this picture on page 484 as we go through this problem. Again, we're trying to find the length of one edge of that cubic unit cell, which we usually denote as A, if you'll recall from our videos on packing efficiency. Now, whenever we're trying to find the length of the edge of a cell, whether it's for packing efficiency or in this case, one thing that we need to do is figure out along which diagonal do we have atoms or ions touching. In some structures, you will have atoms or ions touching along the face diagonal, along the face of the cube. Other times you'll have them touching as they pass through the center of the cube, through the body diagonal. So if we look at this case with cuprous oxide, we've got a body diagonal where all of the ions are touching. So look at that. We can start at the closest right-hand corner and go to the furthest left-hand corner down. And we've got a line passing through all of those radii. So we'll have one radii oxygen oxide, two radii copper ion, two radii oxide, two radii copper ion, one radii oxide, down along that body diagonal. Okay, so what I'm going to do, again, you want to have that picture in front of you if you can, that's helpful. I'm going to go ahead and draw a triangle to represent what's going on here. Okay, so here's the edge of my unit cell, which I'm going to call A. Here's my body diagonal. Again, we're passing through all of those ionic radii. I'm going to call that Y, my body diagonal. And the other leg of the triangle I'm going to call X. All right, that's my face diagonal, is that leg of the triangle. Okay, so now if you recall from the video on packing efficiency for a body-centered cubic cell, I can use the Pythagorean Theorem, which for right triangles says a squared plus b squared, where a and b are legs of the triangle, is equal to c squared, the hypotenuse of the triangle. I'm going to take advantage of this relationship to try to put y in terms of a. Okay? I'm going to try to rewrite x and y in terms of a, but really we want to get to y in terms of a. Okay, so let's see how we could do this. We could say for this triangle I've constructed here where y is the body diagonal, y squared is equal to a squared plus x squared. Okay, great. Problem with that, as you'll recall from that other video, is that we've got x here. We want to get x in terms of a. In order to do this, we need to look at the triangle that's formed between x, this face-centered diagonal, and the other two sides of the cube, okay, or two other sides of the cube, A and A. Now, if this is, at all confusing, I do recommend that you look at the pictures in the book and also that you go back and look at the video for calculating packing efficiency in a body-centered cubic cell. All right, so I can use the Pythagorean Theorem with this triangle too now to put x in terms of A. X now is my hypotenuse. That's equal to a squared plus a squared. X squared is equal to 2a squared. All right, so x is equal to a square root of 2. Okay, now what I'm going to do, take this relationship and come over and plug a square root of 2 in for x squared. Y squared equals a squared plus a square root of 2 squared, a squared plus 2a squared, which is the same as 3a squared. So y equals a square root of 3. Okay, so now I've got y in terms of a. Great. I can also write y in terms of r, because as we saw before in that picture, y, this body diagonal, is passing through all of the radii. So let's remember, if you want to follow along in the picture in the book, you can count how many radii it passes through. If we're starting, pick this book up over here. So again, we're starting at this corner and we're moving down to that far left hand corner. we pass through one oxide radius. All right, so one, excuse me. All right, one oxide radius. And then the next thing we pass through are two copper ion radii, because we're passing through a whole copper ion. Then we've got two oxide radii, and then two more copper radii, and then one last oxide radius. Okay, if we were to rewrite this, we could say we've got 1, 3, 4 oxide radii, and we've got 4 copper ion radii. Okay, so we can look in our problem, and we're given that the radius of a copper ion is equal to 0.74 angstroms, and that the radius of an oxide is equal to 1.26 angstroms. We can substitute these values in for R. Y is equal to 4 times 1.26 angstroms plus 4 times 0.74 angstroms. All right, so Y should be equal to 8.0. Now sig figs are gonna kind of mess you up here. In this case, let's see, how should we do significant figures here? In this case, really all you're dealing with are given values, right? You haven't really measured anything. So let's go ahead and keep with the convention of 2 decimal places in this case, because again, we haven't really measured much of anything. We're just dealing with given values. All right, so we've got 8 angstroms is Y, but remember what we want to find is what A is. Fortunately, we have an expression for Y and A together. All right, Y equals A square root of 3. So we could rearrange this. A is equal to Y divided by the square root of 3 equal to 8 angstroms divided by the square root of 3. So I get that A is equal to 4.62 angstroms.